Hi everybody, I'm going to talk about an interesting characteristic about nines. And we're going to look at a circle too. Have you ever noticed that a circle is 360 degrees and 3 plus 6 is 9? We're going to see that when you divide it in half or multiply it by 2, the digits will always add up to 9. For example, we divide it in half, we get 180, 1 plus 8 is 9. Now, you might think that might not always work if the digits get bigger, but we have to do something called a reduction. So in ancient Hebrew, every letter represented a number. For example, in English, let's say A, B, C, D, E, F, G. Now in Hebrew, they didn't have vowels, and they had 22 letters. But to get an idea of what I'm talking about, each letter might say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they would go to 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, and so on. So every letter represented a number as well. So it's quite interesting. I sometimes imagine, if I said D plus A plus D, I would imagine what it would be like to look at that and think, 4 plus 1 plus 4 equals 9. So just an interesting characteristic of numbers that are connected to each letter in the Hebrew alphabet. And some people do something called numerology, where they would count up all the digits of a word. For example, I could say frog, F-R-O-G, and the F is 6, the R is 90, the O is 60, and the G is 7. And they might add up all the digits and get 156, 163. Now, there were certain numbers that represented certain things, like 40 is known as the number of perfection, or a perfect cycle. But they would do something where they would reduce it to one digit. So 1 plus 6 is 7, plus 3 is 10, and we keep reducing it until we get to one digit. 1 plus 0 is 1. So that would have a number representation of 1. Let me give you another example of what I'm talking about. So let's say we have the number 23. 2 plus 3 is 5. But what about 239? So 2 plus 3 is 5, plus 9 is 14, and then 1 plus 4 is 5. So we continue adding and reducing it until we get to one digit. Now, if I take this number, 1 plus 2 is 3, plus 5 is 8, plus 7 is 15, plus 8 is 23, and we reduce 2 plus 3 is down to 5. Now these are a coincidence that they all added up to 5. So one interesting thing about nines. Nines are interesting because any number divisible by 9, it adds up to 9. So for example, 18. 1 plus 8 is 9. 27, 2 plus 7 is 9. 81, 9. I believe 108. 1 plus 0 plus 8, or 10 plus 8 is 18, which is 9. So if you actually wanted to know whether a number can be reduced or divided by 9 evenly, if you count up all the digits and reduce them this way, if they add up to 9, they will always be divisible by 9. Evenly. So I could make up a number, 3, 7, 5, that's 15, 16, 17, 18. 375,111 is going to add up or be divisible by 9. So let's see, it'll divide evenly. Alexa, what's 375,111 divided by 9?
375,111 divided by 9 is 41,679.
And it's even. There's no remainder. Some might wonder why this happens this way, and it has to do with the fact that we're dealing with the number system that only has 9 digits. We use 1 through 9. We don't include 0 because the only number that will add up to 0 is the number 0. So if I take any other number, 1, 25, any other number is going to add up to something if we reduce it. It will never add up to 0. Everything else besides the number 0 will be able to be reduced. So we can do this reduction method. So let's get back to the circle. If you take the circle, we said it's 360. So we double that, we get 720. We double that, we get 1440, 2880. We double that, we get 5760. We double that, we get 11520. So we keep doubling it, and you'll see it's always going to add up to 9. And it's going to be divisible by 9 as well. So 3 plus 6 is 9. 7 plus 2 is 9. 1 plus 4 plus 4 plus 0 is 9. 2 plus 8 is 10, plus 8 is 18. Well, 18 will reduce 1 plus 8 is 9. 5 plus 7 is 12, plus 6 is 18. Again, reduces to 9. 1 plus 1 plus 5 is 7, plus 2 is 9. And so if we keep doubling it times 2, the number will always be able to reduce to 9, and it will be divisible by 9 as well. So I suppose the question is why? And in addition to the fact that if we add up all the digits and they add up to 9, it's divisible by 9, the fact that we're multiplying by 2 simply means that it's 2 times 9. And then that times 2, then that times 2, it's always going to be divisible by 9. For example, 9 and then times 2 will be 18. But 18 is, right, 9 times 2, so there are 9's in there. And then double that, you get 36. Well, 36 is, if this is 2 times 9, it's 2 times 2 times 9. Double that, 72, or when we saw 720 degrees, it's 2 times 2 times 2 times 9. 144 is 2 times 2 times 2 times 2 times 9. So there, when you double or do the opposite, the inverse, where you divide by 2, you're still going to have that 9 there as part of the multiple. We can go the other direction as well. So if we take the circle and divide it in half, we have 180. So 1 plus 8 is 9. We can cut it again and get 90. 9 plus 0 is 9. Cut it again, we have 45 degrees. 5 plus 4 is 9. We can cut that in half and get 22.5. So 22.5 is 2 plus 2 plus 5, which is 9. And then we could divide that by 2, and we get 11.25. 1 plus 1 plus 2 plus 5 is 9. Divide that in half, and we get 5.625. 5 plus 6 is 11, plus 2 is 13, plus 5 is 18. 1 plus 8 is 9. So because with a circle you can't ever have 0 degrees, we're really using the numbers 1 through 9. And many people don't know why. I don't. They chose the number 360. It could have to do with this modular math. Here's another fun, interesting thing. If you want to find the remainder, which has to do with modular math, if you're dividing by 9, you could actually do this same trick and always find the remainder. For example, 20. 20 divided by 9. 20 divided by 9 is going to be 2, because 2 times 9 is 18, remainder 2, or 2 and 2 ninths. Notice that 2 plus 0 is our remainder, 2. Let's try that with some other numbers. Let's say 30. 30 should have a remainder of 3 plus 0, or 3. Let's see. 30 divided by 9 is 3, and 9 times 3 is 27, with 3 left over. So our remainder is 3. I could take, if you remember, we used the number 375111, and it divided evenly into 41,679. So we can predict the answer. How about 375116? Well, 6 take away 1 is 5. Our remainder is going to be 5. Let's see if it works out when we add up all the digits and reduce it. 3 plus 7 is 10, plus 5 is 15, plus 1 is 16, plus 1 is 17, plus 6 is 23. Right? So that, when we reduce it again, is 5. So because you're dealing with a system of the numbers 1 through 5, I'm sorry, I don't know why I just said that because of the remainder. Because we're dealing with the system 1 through 9, and because everything divisible by 9 evenly, we can add up the digits and find the remainder using reductionism. So when we do our numerology reductionism, whatever it adds up to is also going to be the remainder if we were to divide it by 9. When we look at other numbers, we can also see different patterns. So how about if we divide by 8? So look at 1 times 8 is 8. 2 times 8 is 16, which is 7. So we're going to do the reductionism. 3 times 8. 3 times 8 is 24, which is 6. 4 times 8 is 32. Can you see what's going to happen? 8, 7, 6, 5. So 5 times 8 is going to be 44. So why does it keep going down by 1? Well, because in our system, we're only using 9 digits, 1 through 9. And 8 is 1 digit away from 9. So let's see what happens in the pattern with 7s. 1 times 7 is 7. Now, I can predict that since 7 is 2 away from 9, the next number is going to be 2 away when we reduce it. So how about 2 times 7 is 14, which is 5, 2 away. 3 times 7 is 21, which is 3. 4 times 7, can you see the pattern? It's going to keep reducing by 2, so the next one should be 1. Let's see, 4 times 7 is 28, 2 plus 8 is 10, and 1 plus 0 is 1 when we reduce it. Now what happens if we keep going? Well, we're going to take 1 and we're going to subtract 2. But remember, we're not going through the numbers 1 through 10. So we're going to, let's say, take away 1, we'll get to 0. And we'll take away another 1, which is going to be 9 minus 1, because we're dealing with not 1 through 10, but 9 through 0, or 0 through 9, really 1 through 9. So let's see, 5 times 7 is 35, which is 8, right? So if I do 1 and I subtract 2, then from 1, I take away 1 and I take away another 1 from 9, I get 8. How about the next one? I think it's going to be 6. So we keep descending by 2 because, again, the number 7 is 2 away from our system of 1 through 9. So it's not a system of 1 through 10 that we're used to when we're counting, because we're not using the number 10 or the number 0, really. It's 1 through 9. Let's try one last one. How about 6? So 6 is 3 away from 9. So we're going to descend. The next one's going to be 3, then 0 I could predict, and then 0, well, there's no 0, so it's going to be 9. We're going to then continue. Take away 3 will be 6. Take away 3 is going to be 3. So again, we're really only using 1 through 9 because any number other than 0 will never be reduced in the reduction method to 0. It's always going to be a digit between 1 and 9. So let's see. 2 times 6 is 12. 1 plus 2 is 3. 3 times 6 is 18. 1 plus 8 is 9. 4 times 6 is 24. 2 plus 4 is 6. 5 times 6 is 30. 3 plus 0 is 3. So again, if we started this pattern, 6 then we take away 3, we have 3, and then we take away 3 more, you would normally get to 0, but again, we're not using 0. So we go straight to 9 again, and it would keep repeating. So then in the next pattern, 5, it's going to go 5, and 5 is 4 away, so it's going to be 5 take away 4 is 1, and then we subtract 1, we'll get to 9, and then subtract 4 more. So 9 minus 4 is 5 again. Let's see. 2 times 5 is 10. 3 times 5 is 15. Oh, 6. So if we look at 5, we have 1 times 5 is 5. And we know 5 is 4 away from 9. Oops. 9 minus 5 is 4 away. So we can predict the next one is going to be 4 away, which is 5 take away 4 is 1. The next one will be 4 away. So you would think, oh, well, that's not 4 away, but we're subtracting. So remember, our only options are 1 through 9. So if I'm at 1 and I need to go backwards, I'm going to jump backwards 1, 2, 3, 4, and end up at 6. So the next one I'll jump back 1, 2, 3, 4. It's going to be 2. And then from 2, 1, 2, 3, 4, it'll be 7. So it really isn't as big of a mystery as some make it out to be, especially the 9s. Why is it that we can divide the number 360 by 2 and always get 9? It's some big mystery. Well, no, it's because in the modular math, we're really using it's divisible by 9. And so anything divisible by 9, if you continue to cut it in half, it's going to add up to the 9 digits. So let's just check this. 4 times 5 is 20, which is 2. 5 times 5 is 25, which 5 plus 2 is 7. So, going back to the number 9, it's a wonderful number, but, we really only use 1 through 9 in reductionism. They say that it was only in the last couple millennia we actually use the number 0 as a number. And if you're going to be reducing things to their lowest single digit, you're only going to use 1 through 9. It's not going to be base 10. It's going to be base 9. So it's a neat trick to show people, 360, 720, 1440, 2880, and 180, 90, 45, 22.5, 11.25. And it's neat to show them it all adds up to 9 and claim there's some giant mystery behind it, but really a lot of it has to do with the logic behind the idea of a number system that we're not used to. It's not a 10-based, but a 9-based number system.